Continue. Okay. Quick sip of coffee. Sync clap. All right, let's talk about MPEG today. MPEG is the basis for many, not all, but many of the motion codecs. We talked briefly, I think, about JPEG last time, and JPEG is a still frame codec. In other words, all the processing happens in a single frame. It's for photography. There's a number of photography codecs like TIFF and Targa, and they are strictly intra-frame in that they only deal with the information inside the frame because they're designed for still cameras that were never, and we still consider still images to be separate from each other. But of course, movies, motion pictures, video, film are a series of still images, but they're all connected in time, right? So MPEG is the kind of the most common scheme. MPEG stands for the Motion Picture Experts Group, and this is a standards group that meets and develops and certifies and et cetera, et cetera. MPEG is the basis for H.264 and AVC. And in fact, you could argue that H.264 and AVC are the exact same thing, but they've been named for different reasons. The H-numbered codecs, just FYI, are typically designed by telephone groups for transmission and broadcast. So H.264 would be originally have been designed by the phone companies, perhaps the telephone manufacturers, Apple, Samsung, et cetera. And when I say design, they're simply just certified and stamped with a number, but it really is MPEG 4 underneath all that. And AVC is also the same thing. And H.265 is, again, so you can see that MPEG is the sort of the foundation for many of these codecs, if not the actual codec itself. How does it work? Magic. Yeah, no. It is kind of mysterious, but it uses all the elements of compression, MPEG, right? So it's got irrelevancy, and this is stuff that we can't detect, as I said, or wouldn't miss if it was not there, such as lowering the color bit depth. Now, this one's tricky because we are fairly sensitive if that color depth drops below the point where we start seeing the transitions between colors. And what I mean by that is when you have a light source, a graduated light source that goes from bright to dark, in that image, there's a whole series of changes, steps from one to the other. If you lower the bit depth, you start to see the lines between those steps. So that becomes detectable. So this is where you have to have a balancing act. You want to lower the color bit depth enough to reduce the data, but you don't want to lower it so much that we can see the problem or see the difference, right? You can also reduce the frame rate. Irrelevancy is another example of reducing the relevancy. If you drop the frame rate to somewhere above 24 frames or around 24 frames per second from whatever you started with, you could certainly not notice that those frames are gone, right? Potentially speaking. And these, by the way, these are examples of irrelevancy. These aren't exactly how MPEG does it. I'm just wanting to give you ideas of what you can think of when you think of what's irrelevant. Another one would be audio frequencies. Even though MPEG is a video codec and doesn't deal with audio per se, audio frequencies, if you started chopping off the high and low end, you wouldn't necessarily notice that it's gone. That's irrelevant data, right? Redundancy data, pretty straightforward. It's already stuff we have. So in the case of a series of pixels like we talked about last week, if they're all the same color for 5 pixels in a row, we just record the first pixel, and then we say that don't change anything until you get to the 6th pixel, right? So we have pixel 1 with, say, a certain red. Pixel 2, 3, and 4 have the same red. Pixel 5 has a slightly different red because maybe it's that graduated color, and so we don't bother recording that 2, 3, and 4 pixel because we already have it in pixel 1. But we tell the computer, record pixel 1, don't do anything except repeat that until pixel 5. And that sounds like a lot more information, but in fact, it's way less data. The software makes that information much smaller. And then, of course, there's temporal redundancy, which is sort of the same idea, except we go from frame to frame. All right. And MPEG uses, of course, both of these. So here's that example. Actually, I should have probably showed you when I was talking about it. You'll have 5 blue pixels with a value of 118. This number is just a complete made-up number. And then we just say 1 equals 118, and that's all we say, except repeat 1, basically. The automatic instruction is you don't do anything different until you're told to. So the computer will just repeat, or the software will just repeat that first pixel until you get to the last pixel, which might be now green, and you tell it record new value. And the new value is whatever that number is, right? And remember, if you're confused, by the way, that pixels are made of color. So all you have in pixels is color. The entire image you're looking at is a mosaic of all these different pixels, and all you have is red, green, and blue. Now these are the 3 subpixels. So when we're talking pixels, we mean the entire square, because the subpixels sort of merge when we talk about color data into a common number. So if you take the red, green, and blue and you do a bit of math, you get a single number. So pixels are handled individually, but subpixels are necessary in both the camera and the screens. So it gets pulled back out to the subpixels on the playback, and it gets merged into a pixel on the encode. But pixels are just color data. That's all they are, nothing else. Okay. All right. And again, I should be changing slides while I'm talking. Here's an example of an image that is color pixels. Now we're up pretty close. You can see that this is a Pokemon character. I think it might be Charmander. I'm not exactly sure because it's been a long, long time. But this is what you see, right? So the individual pixels are single colors, right? And if you got even closer, you'd see the 3 stripes of the subpixels. Spatial redundancy only works on still images, just as a sidebar, because it only looks within itself, and JPEG is an example, and motion comes later. So temporal redundancy, we have a frame, 4 shots of the Parthenon. We say 4 of that frame, right? That's all we say, 4 of that frame. Now, inside the frame, things are changing, and we're going to get to that in a minute. But this is the essence of temporal redundancy: is if this was a locked-off tripod static shot and nothing was moving, or it was a still frame in editing, you took a single image and stretched it out for 30 seconds, you'd only get the first frame recorded, and all the rest of it would just remain blank data, because the computer would assume that if it's blank, we're just going to repeat the first frame until we get a new frame or changes happen. Okay. So this is where we examine the space between seconds when we get into MPEG and temporal redundancy. So as I said, we're not recording the similar data across adjacent frames. There's a special kind of mechanism for this, and we'll talk a little bit about this today, in that we have frames with special jobs inside the frame. And we call these frames, and we group these frames together into a cluster, if you will. Cluster is a bad word. Into a group. I'll use the word group because it's a better term. And we have a specific number of pixels of frames, depending on what the resolution of the image is. For things like standard definition and HD, we have 8 frames in what's called a group of pictures, and or GOP or GOP, depends on on your predilection. There are 4 kinds of frames in the group of pictures. There's an I frame, a B frame, there's 3 kinds of frames. There's an I frame, a B frame, and a P frame. The reason you're seeing 2 B frames here, and we'll talk about that in a minute, is the B frames are what's called bidirectional, and they look in 2 directions, so you have 2 of them. But you can also have 1. I'll get to that later. All right. Okay, so again, temporal redundancy, we saw this image, I think, last time. And these are 2 frames that are slightly different in that the fellow's turning his head, his eyes are closed, his mouth is opening a little bit. This is actually a series of images, and I for some reason can't find them anymore, but these are the images that they use to test MPEG. And so you'll see these images all over the internet when you do things like searches for MPEG. So here's the second frame. If we go back here again, here's the frame on the right, frame 2 of the series. And you can see that what the computer has recorded, what the codec is recording, is the frames that are different from the first frame, and those are marked in red. Okay, so the frames that are white, I guess, on your screen, or gray, that aren't, let's just say the frames that aren't red, or green for that matter. I think green's been recorded as well, yes. The frames that aren't red or green aren't recorded. We simply use the frames. The blocks that aren't red or green are not recorded. We simply use those same blocks again. We just reuse them over and over, right? And then if you go in a little tighter, you can see that as well as indicating which frames, or stop saying frames, Mike, as well as indicating which pixels, which groups of pixels to record, which blocks of pixels to record, we also indicate in the data with those little squiggly lines and the little dots, what's moving and where it's moving to, or where it came from, basically, right? Which direction is the motion? okay? And that's called motion change, and we record that as well. So there's two layers of data here. One is which frames have different, and the second one is what's moving and where is it going. Okay, and that's part of the predictive, we'll get into that in a minute, but that's part of the predictive nature of MPEG. Which, by the way, just so you understand, because MPEG does a bit of predictive magic, it also has to store frames before it can record them. This is one of the things that causes lag. So when you're talking about lag in video recordings or live video, the codec sometimes will have lag built into it because it needs to store and hold the data long enough to be able to predict. And it's not really predicting, it's looking, it's hard to explain this, but it's because as soon as you say the word predict, people think you're looking into the future. What you're doing instead is you're taking a chunk of pixels and you're examining them, and you're basically looking into the past. Where did the pixels go to? But that takes a fraction of a second, sometimes as long as 7 or 8 frames and a video, right? And that's a third of a second depending on your frame rate. So that's one of the things that can introduce lag into your images, is that predictive nature. They call it predictive because it's looking ahead as well as behind. So we're calculating direction and speed. The longer the line, the faster the pixel moved, the group of pixels moved. So it gives you the arrows of the direction and also how quickly it's moving, okay? And here's a close-up of that. So you can see there are some that are just dots. Those pixels didn't move much at all. Groups of pixels kind of stayed where they were. What does that tell you? If you look at this and think about it for a second, you see that the background are just dots. There's a little bit of motion. That's probably the camera, by the way, moving, not the background. The building probably isn't moving. Just to be clear, that was a building. If we go back, just to get your reference point, if we go back to the first image, that he's standing in front of a building here, right? So now we look at this and you see that the building's probably not moving, but there's squiggly lines in the foreground. And what is the foreground? It's his head. And so his face is turning, his head is moving. And you can see by the heavy dot that his head is moving to the right on the screen, his left, and part of his head is also tilting downward slightly. You can see lines going up and down. So he's moving his head, kind of tilting and turning. All right. Okay, so each frame has a job. Like I said, there's three types of frames: I frame, B frame, P frame. They're bunched into groups of 8 or 15 or more. There are telephone, I shouldn't say telephone. Telephone's such an old-fashioned word, but phones and internet use longer groups of pictures, reducing, by the way, the video quality, but in order to make transmission bandwidth even narrower, to save data space, right? So, but for video with typically 8 or 15, it's not a finite limit at the 15 end, because as video gets more dense, like 8K starts coming up, they're going to have to investigate going to longer groups of pictures yet. 15 frames was a response to 4K and high-end HD. Originally, it was 8 frames. It was 8 frames for decades, basically from the beginning of MPEG. And then they came along with 15, what's called long GOP, and we'll talk about that, so don't worry. Okay, group of pictures. What are they? Here is an 8-frame group of pictures. And as I said, there's also a 15 frame in video. It's known as a long GOP or long GOP. And what you have here is a repeating pattern of the 3 different types of frames. You have the I, the B, and the P, right? So the I, and I think I might have a slide for this. Yes, here we go. Of course I do. I can tell I was up late writing this last night, some of it. Okay. The iframe is what's called intra-coded, okay? And remember that intra word, because that intra word is a bit of a sales pitch when you're buying equipment. For example, some companies use all intra. We'll talk about that later. You won't probably hear about predictive and bidirectional ever in the marketing language, because the other 2 kinds of frames are a little, shall we say, mathematical, and they're abstract, hard to understand. I'll try to make it clear today. But think of the intra frame, and this isn't exactly right, but as a still image like a JPEG. It can exist on its own. In other words, if you took an intra frame and looked at it, you'd see the picture complete, okay? The predictive frame looks at the previous frame, and you can see that in the illustration here, the gray, that previous frame can be any frame in the string. So wherever you see a P frame, for example, go back 1, you see a P frame here, it's looked at this frame before it, right? Or maybe this one, it's looked at one of the frames ahead of it. And in this case, you can see these 2 little hops. This P frame is looking at both of these B frames. right? And when I say looking at, what I mean is it's comparing itself with those other frames. Now here's where it gets a bit weird. The B frames are what's called bidirectionally predicted frames or bidirectionally coded frames. And what they do is they look in both directions. Both of these types of frames require math. Without math, they don't exist. And what that means is if you look at this string, these are 7, when I say 8 frames in a group of pictures, I mean 8 video frames. So if we're looking at 30 frames per second, this is 8 of those frames in MPEG. What, if you think about it for 2 seconds, okay, now you've thought about it for 2 seconds, that first iframe and that last one, which is the first iframe of the next series of 8, are the only frames of video in these 8 strings. Right? Does that make sense? The other frames, the B's and the P's, are strictly math. They are not data recorded in the proper sense. The iframe is a snapshot, an actual, basically, it's an actual still frame from the sensor, entirely complete. The B and the P frames use a lot of math, and they analyze the sensor data as well, because they want to see what's changed and what's moved, and they create themselves. If you were to stop and examine, let's say, B frame number 4 here, you wouldn't see a picture. You'd see kind of this, right? So if we look at the iframe as being a complete image, and I'm sorry this is quite crude, but you get the point. The first B frame is big chunks missing, right? Because it's only the data that's changed based on the first frame. The second B frame is kind of looking back at the first B frame and the P frame, and it's the data that has changed and will change, right? And don't worry about all this kind of, it's very abstract, and I'm sure that people are already starting to drift away because even I have a hard time putting this into words. But basically what's happening is that the only frame that's an actual frame of video, the only frame that you could edit on is this iframe. All these other frames don't exist. If the math were to break down, these frames would vanish or become irreparably damaged. This frame here, this iframe, doesn't require math. It's the sensor data, boom, right? So this is the first big shortcut that MPEG takes. It really only records one actual frame every 8 frames. And then it does a whole bunch of comparisons. Okay? That saves a whole pile of data. And using software and all kinds of other tricks, we don't really notice that those other frames are artificial, right? Until it breaks down. And let me just see, I think I've got, yeah, here we go. I think I've got this here. Yeah, so let me show you this. I'm going to stop share. Hoping this won't get taken down because I don't think there's any sound here. Let's show you. Oh, where am I? Where did I go? Here we go. Let's show you this. Okay, full frame. Right.
Yeah.
Yeah, we don't really need the sound, but I guess we're going to get it anyway.
Sure is good drinking with the boys.
Okay, so let's go back. What happened here? So first off, this is a damaged frame, right? All this information you can see where the blocks and squiggles and stuff are corrupted data, bad math. Something's happened here. I don't know what, and it doesn't really matter what. But what happened right here? One of the iframes disappeared and became black. All right. And then the computer tried to rebuild the next 8 frames with that black frame as a basis. And look what happens. You get that kind of curtain effect. Right? I'm going to go back again.
I'll drink to that.
What's happening is as the motion, so it's only recording what's moving, right? The MPEG is only recording what's moving, things in the background that are static. So as things in the foreground move, they sort of draw in the missing areas, and you get this.
I'll drink to that.
It will eventually stabilize.
Say, go ahead.
This is a
How
terrible.
did the twins do that? Oh, it was too much. They were falling all over the...
Gordy, didn't know you had...
No.
All right, so that was kind of a crappy one. Let me see what else I've got here. Just get rid of that. Okay. Bear with me here. I had a better example and I don't know. Oh yeah. Here, I'm gonna, okay, you know what? I'll carry, I just got something to show you guys in a second. Let me carry on. All right, where were we? Okay, so if you remember that the iframe is an actual frame. The B and P frames are frames, they're virtual frames. They're mathematically based, all right? When you have compression, when you compress these frames, you can see that the iframe, for example, the compression ratio, in other words, the ratio of actual data versus the ratio of recorded data is 7:1. So 7 times less data than the original frame. So that's using all spatial compression inside the frame, like a JPEG, right? Not a very good compression ratio. You still get a fairly large frame. But when you think about the fact that the P and the B frames are just doing a lot of math and a bunch of comparisons, the actual data compression is much, much higher. It's 20:1 on the P frames and 50:1 on the B frames. So the average of all the frames is somewhere in the neighborhood of 27:1. I mean, these numbers aren't hard and firm, but this gives you an idea that when you average out the compression between all the frames, you gain about a 4 times advantage over just a strict I frame only. Now, why this is important is there's a lot of codecs, a lot of MPEGs that are I frames only. Again, we'll talk about those in a minute. And they have a much lower compression ratio. They're more close to that 7:1 number, which means your files are big, lots of data, right? All kinds of reasons to be careful about choosing that. All right. So before I move on a bit, I'm going to move on to macro blocks because I've been talking about these pixels that we're examining. I want to get into what that actually is. Are there any questions about the IP and B frame? Like you totally get it, right? Totally understand it. Wow. No chat. Nothing. Nothing. Okay, well, I'm glad to hear it. All right. Macro blocks then. So when I talk about the pixels that are being examined, it's not just a single pixel, right? It would be impossible to dictate, examine motion as soon as an object leaves the pixel. So in other words, in order for us to use the motion data, we have to look at more than one pixel. We have to assume that the object in the frame is going to move more than a single pixel, and it does. And so we create these things called macro blocks. And they're 8x8, they're 16x16 pixels per block. And what you do with them is they have what's called a reference frame. And this is kind of reversed. But the reference frame looks at a chunk of the object, right? So when I say looks at, I mean the math is examining. And so remember, this is all happening in cameras and in playback all the time, right? There's tons of processing going on, which is why your fans go crazy, which is why you only have so many layers of video you can edit in Premiere, which is why your camera can only record so many frames per second. These are the reasons for these limitations is there's a whole ton of math. And so one of the math things that is happening is that a chunk of the image is being examined. And so in that reference frame, we look at one portion, and you see that portion actually crosses over a bunch of different pixels, right? Which is why we have a macro block, because then we can look at this thing crossing through 8x8 pixels. We have this shape, and then the target frame where the object is going to, like it's moving down to the left, right? We look at that, we find that same shape in that target frame, and we do a bunch of math, and all this stuff on the right is just a bunch of math, to come up with a formula to indicate how fast and where it's going. That's kind of all I'm going to tell you. That that DCT quantization entropy coding, that's serious high-level math, and you don't need to know it. Other than you have to know that there's a lot of complex math going on, not just per frame, but in these macro blocks. So if we go back to that video we looked at before, and you saw those little black squares, those are the macro blocks. And in fact, let's do that for 1 second. Let's just switch. Oh, hang on. I should, before I switch, I should get the video ready, shouldn't I? Yeah, so let's have a look at this. Let's just find a different chunk. Right there. And then I'm not even gonna make it move. I'm just gonna share it and stop it. Don't need sound. Share. Oh, there we go. So full frame. Now you see these squares, and there we go. You see this is weird how much delay there is. If you see these squares that are here, like these are actual squares. These are the macro blocks. And I know it's really tiny and it's hard to see, but where that little pixel's kind of dancing around, those are actual squares. And those squares are the macro blocks. Those are the 8x8 or 16x16. I don't know, I can't tell from this, chunks of pixels. And that entire frame that we're looking at with these people at the table and the bar is divided up into not just pixels, but groups of these macro blocks. Those macro blocks are what MPEG is examining. When we talk about spatial redundancy, that's what it's looking at. It's not actually looking at any two random pixels side by side. It's looking at them in these organized blocks, all right? So that's what that's all about. Okay. Go back to our show already in progress. Okay. Share. All right. So macro blocks, there they are again. Now we look at this picture. So now when you see this picture with the red squares, maybe it makes a bit more sense. These are not pixels. It's blocky on purpose because these are groups of pixels, macro blocks. All right. We record the original location, the new location, and the speed using this method that we saw here. Right. This is where the speed and direction information comes from. What's in the frame, what's changing is obvious in the sense that if there's data there, there's data there. Like in this example, this pixel has data. This one does not. Right. So that's pretty straightforward. But the motion and speed is calculated using this comparison method and all this blah, blah, blah here. Okay, macro blocks. So I said that. And so one of the reasons you cluster the pixels together is that it improves the accuracy of the math, right? So not only is it obvious that an object is going to move more than a pixel on an image, and sometimes it moves dozens and not hundreds of pixels at a time, but it's just better for the math if you have more things to compare. So macro blocks, 16x16 gives you better math than 8x8, right? So those are the kind of things you can come up with. One isn't better than the other. It really depends on what your application is, because bigger macro blocks will mean that data could be less precise. Here's an example of macro blocks in action, where we take a frame with the football player's helmet, and that's a block of 16x16. The football player in the next frame, n+1, moves to the right of your screen and down a bit, and so that block is now moved there. The search area is the area that the MPEG data is assessing, looking for macro blocks inside that area, and then it does a bunch of math, right? That's kind of the whole macro block story in a nutshell. Okay, so good compression uses all the tools that it can, and MPEG is one of those good compression schemes. It's very efficient. It's fairly standardized. It uses spatial coding or intra-coding within the frame, intra within, and temporal coding or intercoding between the frames, right? And combines the two. And that little bottom diagram kind of shows you the diagram comparing the both sets of compression together to get it output. All right. And that's, again, same thing. So spatial redundancy, just again to repeat, looking at these, this is again our reference frames. Within the frame is looking at that chunk on the wall. Temporal is looking at the two frames together. And there's a whole pile of other stuff being done as well as that, like math. All right. So let's talk about groups of pictures. So the groups of pictures are the sort of building block of the frames. If macro blocks are the building block of an individual frame, the group of pictures is a building block of time. And long GOP or long GOP is used in HD and 4K. It's usually 15 frames and can have different patterns of I and P and B. Okay. There's three kinds. The more B frames you get, the better compression you get, because if you understand that the B frames are calculated looking at two other mathematically calculated frames, there's way less data but way more math going on, right? The I frame is a standalone frame, no calculation required. The P frame is looking at simply the I frame, right? It's predicting itself based on the last real frame that it looked at, or as you go along the word, it looks at the previous P frame. It's not looking at the B frames the way the B frames are looking at each other in the P frames. So, long rambling way of saying that the I frames have the least amount of math, the P frames have an intermediate amount of math, and the B frames have tons of math. And the more math, the less data is being stored. but the better you have to have your compression scheme and your hardware to make it all work. Typically when compression breaks down, it's the B frames that break down first because they depend on the math exclusively. Okay. There's two kinds of GOPs or groups of pictures. One's called open, and that one looks at the next GOP, particularly for things like streaming. This is really handy. So streaming codecs, variations of MPEG for streaming will have an open GOP, and that means that the B frames at the end are looking at the next I frame, right? You always start, by the way, you always start a group of pictures with an I frame, but you'd never end one with an I frame. There's only one I frame, kind of like a mob movie, right? There's only one capo in the room. There's only one chief, and that's the first I frame. So the open GOP or open group of pictures is looking at the next group of pictures and the first I frame in that next group of pictures. And that gives you better data between frames. So for streaming and things like that, it's more what's called robust. It's harder to break the picture down because the frames are linked, the groups of pictures are linked. For editing, however, that's a bit of a problem. You want a closed group of pictures because you might truncate, you might separate these two groups of pictures when doing an edit, and you don't want one to break down if you break them apart. So closed groups of pictures don't look at other groups of pictures and often end in a predictive frame. Not that that last part's important, but that's the difference between open and closed. So it's still the same structure. It's just that it's looking at the next one, and closed is not. So here's the one that we like a lot for editing, and that's called an all I frame or an all intra frame. So when you look at, for example, AVC intra, that is a MPEG with no math being done, right? I shouldn't say no math. That's an exaggeration. But the frame reconstruction math is not happening. The frames are all independent iframes. It's though they were a series of JPEGs, and in fact they kind of are, because all the frames that are in an all iframe stream are simply spatially encoded. There is no temporal processing. Well, probably not none. There's probably some, but they're not looking at each other to compare data. They're looking at each other for other reasons, okay? So the visual data is strictly spatially created. It makes for big files. It's very poor for the web because, as you saw before, the compression is very low in that you get 7:1. So just so I'm clear, low compression means higher quality. High compression means potentially lower quality. The more compression you're doing, the more math and processing you're doing, right? But what's good about an all iframe group of pictures is you can edit anywhere. Okay. And let me just go back and clarify this. So when I talk about a 15 frame group of pictures, if this is a 30 frame video, this is half a second. And you can only edit technically at the iframe because you can't break the group of pictures up, right? So this is one of the problems with MPEG as an encoding scheme for things like editing. MPEG was never really designed around editing in the first place. It now has adapted to one of these models here. We'll get to this in a second. But if you imagine that you're editing this, if you make an edit at the 5th and 6th frame, that stuff we saw in that video where it all breaks apart, that happens. So what the software has to do, what your editing software has to do, is it has to create an iframe at every edit, right? If you're editing, so this is why you have what's called edit codecs, and we'll talk about that a little bit as well. But if you don't have a codec that's designed for editing, if you're just editing the raw MPEG stream, then your computer has to put in all the extra frames and rebuild the picture and start the group of pictures again. So it will rearrange these frames, and understand that's math, that's processing, that's even time, that could be rendering, it all depends. It might be, nowadays it might be almost unnoticeable because computers are getting so quick. But it does put an extra burden on the software to include an iframe at every edit. So back in the bad old days when I was editing, computer editing in the Avids years and years ago, when this was sort of a new idea, the more edits you would do to a file, the larger it would get. So if you had a file that was 1 megabyte in size, and you edited on it for like an hour, you could end up with a file that was 1.5 megabytes in size, and yet it's still only 30 seconds long. Because you've added all these iframes every time you put an edit in, right? That's still happening. It's just seamless to you now because software is getting so much faster. But there is a cost in compression. So then what typically has to happen at that point is when you finish the edit, you have to re-render the entire timeline to have a continuous series of iframes. So you re-encode it, right? That's, again, that's Dave Barenbaum might be talking to you guys about some of that. What's they call it? Sometimes they call it intermediate codecs or mezzanine codecs. That's a lesson for next week for us. But anyway, so understand that iframe, when you see cameras that advertise all intra editing, they're recording all iframes, which means it's less processing in the camera because there's less math going on. It's easier to edit, but it's harder to stream that result. So you've got to re-encode it when you're finished, right? Price, speed, quality, or as they used to say, pay me now, pay me later. Okay, so here's a couple of examples. Panasonic has what they call AVC Intra, which is MPEG 4, right? Which is also H.264, really. But AVC Intra 50, so what they do, because they recognize that all intra codecs are huge when it comes to bandwidth, they limit the bandwidth, right? So they increase, what they're basically doing here is they're decreasing the resolution in each frame, and here's how they do it. AVC Intra 50, now there used to be an AVC Intra 25, and we may still have a couple of those cameras. That's really horrible looking, by the way. But they're all iframes, so you can edit anywhere you want. AVC Intra 50 is 50 megabits per second bandwidth limited, right? And what they do, the couple of tricks they do to achieve that is they reduce the color sampling. They don't change the bit depth, but they change how often they sample the colors. So in other words, the bit depth dictates how many colors there are. Those don't change, but what does change is how often they sample the colors. And that varies from every second to every fourth frame. You know, again, we'll talk about that later when we talk about codecs. They also change the frame size, the dinks. They reduce the frame size by 3/4. So you're shooting 1920 1080. The camera says it's 1920 1080, but as soon as you switch to AVC Intra, you're only getting a 1440 by 1080 picture, right? That's how they achieve a lower data rate with all iframes. In AVC Intra 100, the frames are not resized. They're fixed and they're not scaled, right? The color sampling is still played with a little bit because 100 megabits per second still isn't full bandwidth, but they've also deleted data before this has been encoded, okay? So just, again, the point of this is to understand that don't just willy-nilly pick codecs without understanding what's gonna happen to your image, especially if you're doing like special effects. If you're doing a sci-fi or some kind of green screen or effects video, you don't want that color sampling reduced because it's gonna make it very hard to do color work and to do, you know, color picking and things like that, right? Because color samples are gonna be sort of not corrupted, but they're gonna be reduced. All right. A couple of other examples of iframe codecs, IMX, right? So Avid uses IMX, Apple uses ProRes, and then there's something called MJPEG or Motion JPEG. These are all codecs where every single frame is a real frame and you can edit anywhere, okay? Remembering that, and I'm gonna go back in case you forgot that in this situation with a regular MPEG, streaming MPEG, non-iframe MPEG, in other words, non-all iframe MPEG, you can't, well, I shouldn't say you can't edit anywhere. The software will let you edit anywhere, but it then fixes your mistake, right? Basically what's happening here is that instead of if you think of the iframe as a door, you can walk through whatever you feel like it. The other frames are walls and you can walk through them, but then the software has to patch the hole and build a doorway, right? And that takes time. So you basically punch a hole through the frame, like at the 5th or 6th frame. It's got to build iframes and create an opening for an edit, okay? Is MPEG perfect? No. Can temporal redundancy be ineffective? Absolutely. Codecs like MPEG are poor when you have many cuts, fast edits, like super fast edits. When there's lots of motion, camera motion, you know, again, an all iframe would be better than a PMB frame style MPEG when you have like car chase scenes and moving cameras, because all that blur, remember, all that blur means every single pixel in the frame is changing. Blur, by the way, when you add blur in Premiere, blur affects, if depending on the blur you've chosen, can affect every single pixel in the frame, which just makes the whole frame much more large in data, right? Because now every frame has to be every pixel has to be recalibrated every frame. So adding blur used to be a real burden. Now not so much. Fast motion, and it's not archival quality. So when you're storing something for long-term archives, you often don't use MPEG codecs. There's other specialty codecs for archive purposes. Okay. And that is MPEG. So that was That was the lecture from last week. The last handful of slides expanded to hopefully be a bit more clear.